Hello, I'm Katie Steckles.
And I'm Peter Rowlett. And Katie, what's today's mathematical object?
Well, today's object is a Rubik's Cube, which is, as some people may or may not believe, a mathematical object in very many ways. So this is something that is sold in shops as a toy and very much marketed as such. But if you're a mathematician who understands a bit of the maths behind it, it is one of the most shining examples of a beautiful abstract mathematical notion that you can possibly imagine. So...
Yes, I don't know an awful lot about the maths behind it. I remember a few years ago somebody said to me, I'm struggling to work out how to teach group theory to my undergraduates. And I said, aha, Rubik's Cube. But that was about as much information as I had on the subject. So I have one. I sort of don't know how to solve it and I don't know how to do maths with it, but I have one anyway.
Well, if you go to the Wikipedia page for group theory, there's just a picture of a Rubik's Cube at the top,
nice.
Which... I guess it cements the idea that it's connected somehow to maths. I think as an object, people think of it as a puzzle and it's a toy. Like originally the marketing on it was very kind of, we made this thing and it's interesting, have fun.
Right.
And the makers of the Rubik's Cube didn't know how to solve a Rubik's Cube. They just knew that this was a thing and they were quite impressed with their ability to make a thing that can turn in all the directions without falling apart, which I'm still blown away by. I don't understand the engineering of this at all. This is a
No, I know.
Object.
Some magic happens in the middle of the thing. So does that mean Mr. Rubik didn't know how to solve his cube?
Nope.
Right.
Nope, they just put it in a box that just said good luck. And I think nowadays if you buy a Rubik's Cube, it comes with a little booklet that's got instructions for how to solve it, and there's any number of online tutorials and videos and things. But it really was just, here's a thing, and it was the first people who actually properly took this thing and played with it properly. People who were having fun with it, whatever, but people who properly played with it and did maths and came up with notation and came up with rules about it were mathematicians.
Proper fun with it, right?
Yeah, exactly. And, coming up with algorithms for solving it. And it's the kind of thing you can do yourself sort of experimentally and figure out a thing that works. But if you actually pull this thing apart, not literally, obviously, but, conceptually pull it apart, you can see how the kind of structure underneath it sits together, and it's quite pretty. So I thought I'd try and explain a little bit about how that stuff works.
Mm-hmm.
This is the kind of maths that most people don't necessarily encounter unless they go to university and do maths. So it's, without any visual aids or the ability to write anything down, this is going to be great.
Yes.
So you mentioned group theory, and a group is a kind of mathematical structure. It's a sort of a notional object that mathematicians think about. You're probably familiar with groups in the sense that you use them all the time, but you don't realise it. So the definition of a group, the thing that you need for something to be a group, is that you've got a collection of things and you can combine things from the group together. You can take two things from the group and say, I'm going to add this one to this one. I'm going to combine them together. If you do that, the thing you get should also be in the group. Mm-hmm. So the sort of classic example of this is the set of numbers. And as a simple one, you could say just the whole numbers, just the integers. If I take two integers and I combine them, I'm going to say my combining method. I actually used the word add a second ago, which was slightly a slip. But your combining doesn't have to just be adding. It could be anything. In the case of whole numbers, it is actually adding. So you can add together two whole numbers and you will always get a whole number.
So the set of whole numbers is not a group, but when you have to combine it with the operation, which is add.
Yeah, the definition of the group includes how you're combining the things.
So you said the set of whole numbers with addition, but it has to be addition, so it can't be multiplication. Why not?
No, well, I guess if you take two things from the set of whole numbers and multiply them together, you do, assuming you've done it right, also get a whole number. But there is another thing that you also need. So there's the proper definition of a group includes a few other bits as well. So you need the operation that you're doing to behave in a sort of sensible way. So you need a property called associativity, which is to say if you've got two things and you add them together and then you add a third thing, you get the same thing as if you added the second two things and then put the first thing on as well. So like A plus B in a bracket plus C is the same as A plus B plus C in a bracket. Kind of, it doesn't matter like what order you do the operations in, like combining them.
Yep.
It also you need to have a thing in the group essentially that is the equivalent of 0, right? This is called the identity, and if you combine anything with that element, you don't change it. So in the numbers, if you add 0 to something, it stays the same. So we call 0 the identity of the group, and it's a special object within that sort of system. It's got this special property that it doesn't change anything, but it also kind of gives you an anchor as like the beginning or the middle of the group, I guess, whatever it's the special point in the group. So for instance, if you've got a number like 4 in the set of whole numbers, you've also got a number like -4, and if you do 4 plus -4, you get back to 0. So we say that -4 is the inverse of 4, because if you combine it with 4, it gets you back to the identity. In the case of multiplication, if you try to do this, it doesn't necessarily work. So there isn't an object in the whole numbers that is the inverse of 4 under multiplication, because if you wanted to have the identity element there, it wouldn't be 0 anymore. If you multiply something by 0, it does change. If you multiply it by 1, it doesn't change, so you could think of 1 as the identity there. But if you've got 4 and you want to find the inverse, that would be a quarter, because 4 times a quarter is 1, and a quarter isn't in that group. Like, it's not an element there. So you would either need a bigger group that contains more things, that also has all the fractions in as well, or you would need to use a different operation like addition. So hopefully that gives people an idea of roughly what a group is. The group of numbers is an interesting one because it's infinite. There are infinitely many numbers in the group, but you can do this kind of thing in finite sets as well. So if you think about the numbers on a clock, hours of time in the day, the numbers run from 1 to 12, but you can sort of think of 12 as 0 in some sense, and 12 would be the identity in that group, because if you add 12 hours to the time, you get the same time. And you can say add 4 hours and that'll take you part of the way around the clock. -4 hours would be the inverse, but -4 is the same as +8, if that makes sense.
Yep.
So it's sort of called clock arithmetic. Sometimes you think of it like a finite set of numbers that you can do this stuff in, and you can add them together, and you always get a number that's on the face of the clock, but they don't necessarily work the same way as whole numbers, because you can't just keep getting bigger and bigger. They kind of wrap round. So the Rubik's Cube, which is the reason we're here, is a really interesting example of a group. And in this case, it's a bit more conceptual, so it's not so much numbers and adding. So the elements of the group associated with the Rubik's Cube are either, there's 2 ways to think about it, moves that you do on the cube, or equivalently, configurations that the cube can be in. So if you've got a scrambled up cube and you look at it, that is one possible state that the cube could be in. And it's equivalent to starting with a solved cube and applying the move that gets you to that state. So the moves correspond to the states, in the sense that if you start from a solved cube and do the move on it, you get one of the states. So those 2 sets of things are equivalent. There are quite a lot of them. It is a finite group, because this object is finite. I don't know if you noticed, the Rubik's Cube is a finite object, but you can't just keep doing lots of different things. You'll eventually get back to the same thing. The total number of possible states that the Rubik's Cube can be in is 43,252,374,489,856,000. And yes, that is my job. I've memorised that number because it's my job. But it's a big number. It's 43 billion.
Yes, don't you have a party trick where you solve the cube reciting facts about it? Is that right?
Yeah, I know a terrifying number of facts about Rubik's Cube world records. So my world record for solving the Rubik's Cube while reciting Rubik's Cube world records is around about 2 minutes. But I could definitely do it faster. I just don't want to not say any of the facts because they're all interesting. I'm not going for the fastest time. It's the world record for doing it the best. The cube has a lot of possible states it can be in. But I think this is kind of interesting because it tells you something about the way this group is built up. So when you have an object, an element within a group, you can multiply it by itself. And if you do that enough times in a finite group, you'll get back to the identity. So the identity on the Rubik's Cube is obviously a solved cube, because that's your kind of 0. But say you're on the face of a clock, 3 hours. If you do another 3 hours and then another 3 hours and then another 3 hours, you get back to 0 again. So we would say that the order of that element in the group is 4, because if you do it 4 times, you get back to a solved cube. And on the Rubik's Cube, I'm about to create some audio here. This is proper podcasting. If I do a quarter turn on one face, like that, hopefully that came through on the recording. And if you can't see this Rubik's Cube, which no one can, just imagine a Rubik's Cube on which I've done a quarter turn on one face. That itself is an element of this group. It's a move on the cube. If I repeat that same move 4 times, so that's 2, 3, 4, you can imagine I've now got back to a solved cube. So the order of that element is 4. But then if you start combining things, it gets a bit more interesting and maybe gives you a sense of how it is that you could possibly have 43 trillion different things just by turning the 6 faces of a cube. So if I do a turn on the right-hand side of the cube, followed by a turn on the top of the cube, so 2 adjacent faces, and when I say a turn here, I always mean clockwise, because this is the notation that mathematicians came up with. So a clockwise turn on the right face and a clockwise turn on the top face. That gives me an element that I can then repeat. So I do right top, right top, right top. And the number of times I repeat that pair of moves till I get back to solved. I can never remember which way around it is, but it's either 63 or 105. I mean, I could do it right now, but this is a short podcast, so it's fine. But if I, instead of doing right top, I do right and then top anti-clockwise, so I just switch the orientation of one of those moves. So I do the right face clockwise, top face anti-clockwise, and repeat that, it's the other one. So one of those is 63 and the other one is 105. It's really fascinating to me that such a small change can completely alter the kind of properties of that move and the way it behaves. And obviously on the cube you've got inverses, because a quarter turn is a single move, but the inverse is turning it backwards, turning it anti-clockwise. It's clockwise as you look at each face as well. So if you're following Rubik's Cube instructions, you've got to kind of put the face that you're looking at square onto you and turn it clockwise or turn it anti-clockwise.
And is turning it,
depending on what it says.
Is turning it anti-clockwise different from turning it clockwise 3 times? No, the same.
That would give you the same thing, yeah.
This is in the territory of Paul's famous blog post on this subject, isn't it?
Yeah, so this is on the, if anyone's a regular reader of the A periodical, we have one post that is consistently the top viewed post on the entire website for an incredible reason. So he wrote a post about the Rubik's Cube because he's a group theorist by training.
This is Paul Taylor, we should say.
Yeah, just one of our authors on the site, and it's about how if you have an element of a group, it will always, if you repeat the same element enough times in a finite group, it will always get back to the identity. And this is like a really fundamental idea in group theory, but the Rubik's Cube illustrates it really nicely, because if you take any combination of moves whatsoever, so it could be a single turn, or it could be 2 moves, or it could be a 16 move sequence, if you repeat that sequence enough times, you will eventually get back to a solved cube. And it's lovely. And it may be that you have to repeat it, several hundred times to get back, but it will still work. So the point that Paul made was, if you've got a solved cube and you repeat the same move on it over and over, it will get back to a solved cube. And the title of the post, which we sort of did a bit tongue-in-cheek, was How to Solve a Rubik's Cube in One Easy Step. Which is great, except that anyone who's searching for how to solve a Rubik's Cube and is looking for a bit of a shortcut ends up at this blog post. And because
and then
so
gets
many
annoyed
people,
about it.
Yeah, the comments are just full of people going, well, this is no use. My cube isn't solved to start with. Well, yes, that's not the point. If your cube is not solved to start with, you're going to have to solve it first, then look at this blog post. Yeah. So it generally gets a few hundred hits a day. It's quite a nice driver of traffic to the site, to be honest. It's probably improved our Google rankings quite well.
I don't know. It's a bit troubling that so many people are searching for this information, and what they're finding is, not it. Well, presumably people searching how to understand group theory are not finding it. They're the ones who could do with it, right?
I mean, I hope they are, because it's a really nice little post. But it makes this point, and it's really nice. So the reason it happened was because I think at one point Paul was sat in his office just absent-mindedly playing with a cube, and he did a thing where he turned one face of the cube and then rotated the whole cube, and then turned the next face and rotated it a quarter turn each time, so that he'd kind of gone round the outside of the cube. And then he thought, I wonder how long I'd have to keep doing doing this to solve the cube again, because obviously at some point it will come back. And I think the answer we got was it would take you quite a while, but that's what you would expect. It's a big group. There's a lot of elements in there. But the fact that you can look at these moves and see how they interact with each other means that you can make predictions about this. And if you use, group theory software, there's programming languages designed for group theory, you could put in the details of how each of the moves behaves and combine them and see what you would get, which is what we actually did for that blog post. So that's kind of fun. So when people professionally solve the Rubik's Cube and come up with these algorithms for it, they're probably not thinking about group theory, right? People who are speed cubers, you get these kind of terrifyingly brilliant 12-year-olds that are superbly fast at solving the Rubik's Cube. The world record is like 2.5 seconds or something ridiculous. Right. I think it's under 4 seconds now. Was the latest record. It's just ludicrous.
And that's for you've sort of looked at it and seen what you need to do, and then you go, right? It's not sort of the thinking time necessarily.
And it's an arbitrarily scrambled cube as well. It's not just there's a couple of moves to do on it. You might think, it was just an easy one,
right? Yeah.
But they also do best average, where you get 10 cubes and you solve them all, and they take your average time, and that is still kind of sub 8 seconds, 7 seconds.
I mean, it's just terrifyingly good to see, isn't it?
Yeah. I mean, it's just a very niche skill.
Yes.
But the people who do this are not necessarily thinking in terms of group theory. But there are some nice bits of group theory that you can use to understand the structure of this a little bit. So one thing that is different about the Rubik's Cube group compared to the group of numbers is that it matters which way round the moves go. So if you're adding together numbers, 2 plus 3 is the same as 3 plus 2. And in a group, we would say that these two elements commute with each other. In a group like numbers, all elements commute with all other elements. So, it doesn't matter what order you put the numbers round, you'll still get the same answer. In the Rubik's Cube, it does make a difference. And if you've got a Rubik's Cube handy, if you do a turn on one face and then a turn on another face, that obviously not the opposite face because those two moves are separate, but on an adjacent face, you see what you get, undo both of those and then do them the other way around. You'll see you get a different configuration of the cube. And it matters what order you do them in. And this is a property that some groups have, but it means that depending on which moves you use, they will give you a different result if you do them in a different order. Some moves do commute with each other, so opposite faces, you can quite happily do moves on the two opposite faces of the cube in whatever order you like. And there's a thing in a group called a commutator, which is sort of a measure of how much two things commute with each other. So if you've got two moves, say one of your moves is A and the other move is B, whatever they might be, if you do A, then B, then the inverse of A, then the inverse of B, then this is the commutator of those two moves. And if the two things commute with each other, so if it doesn't matter which order you do them in, this is just the identity, because if you think about it, you've got A and inverse of A, and you've got B and inverse of B, and they kind of cancel each other out. So if the two things actually commute, and it doesn't matter which order you do them in, then you get the identity. If they don't commute, then the commutator, in some sense, will tell you how much they don't commute. I guess it's kind of like the more big and horrific the commutator is, the less these two things actually commute with each other. But when you're designing Rubik's Cube moves, you can use commutators. Because essentially the way that Rubik's Cube solving goes is that you get some bits of the cube and you put them in the right place. And if you're starting off, you could maybe do the top of the cube, get a whole face of the cube sorted. But then every move you do is not just going to move the piece that you're putting in place, it's going to move the rest of the cube as well. So once you've done the first layer, it's probably possible to do maybe even the first two layers without kind of too much hassle. But once you're trying to do the third layer, you're going to just mess up the stuff you've already done. But if you apply a move that is a commutator to the cube, then because you're doing a thing and then doing a different thing and then undoing the first thing and undoing the second thing, that will quite often put back pieces that you've moved. So this is the basis of a lot of these algorithms, is that you take two moves on the cube, one of which is the thing that you want to move. I want to put this bit there. Okay, fine, that's one of your things. And then the other one is something else. And if you put them in a commutator, you actually kind of do the thing that you're doing, but while putting back all of the bits that you messed up while you were doing it. And it's quite a nice thing. And if anyone's a serious Rubik's Cube solver, they will probably have memorised several algorithms. If you write those algorithms down and look at them, you might notice that they are actually a thing, a different thing, the inverse of the first thing, the inverse of the second thing, and you didn't even notice it.
Right.
Like it's just a word that you've memorised in your mind, but that is actually how it works. So I think that's a really nice sort of, it's the kind of the interface between something that's a hobby and then this really nice sort of machinery that sits underneath it.
Yeah, and that's definitely the bit where it feels like it's getting too much for your brain, is that you've solved some of it, but then you've got to kind of keep that in place while also doing some other stuff that interferes with it. And it's nice,
I mean, if
mathematical machinery behind that.
If people ask me about solving the cube, I always recommend that they start off by trying to get one face, just because it gives you a lot of insights into this. So you might want to get the white squares all on one face, but you need to do that in a specific way. You can't just put any of the white squares anywhere within that kind of face. Like you need the one that's a white square with an orange square on it to be between the white face and the orange face. Like the centres of the cube faces don't move, so the white one is always next to the orange one and the blue one, assuming you have a standard UK Rubik's Cube and not the other type of Rubik's Cube that has a slightly different arrangement of faces. Like two standards out there anyway. But there's always a white-orange edge piece, and it always goes between the white face and the orange face. You can't just put that anywhere on the top, you have to put it on that side. So once you've sort of seen that and built all of that stuff, that's a nice sort of way to start. But then, once you get to the other bits, you then start having to look up these algorithms and maybe memorise them, or at least follow them from a piece of paper.
Okay, so we're on Twitter individually. I'm Peter Rowlett.
And I'm at Steckles.
And together the podcast is at Maths Objects.
Both of us blog at aperiodical.com, which is where the podcast is hosted.
And if you want to contact us, if you want to suggest any objects or talk about the Rubik's Cube, you can email objects@aperiodical.com.
The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.